what are conformational isomers? We know that if you have a carbon-carbon single bond, and around this carbon-carbon single bond there is a free rotation possible, and due to the free rotation around this carbon-carbon single bond, we will have a different relative position of atoms attached to the two carbon atoms. They may have different spatial arrangements. The relative positions will be different. Those relative positions that you get by the rotation around the carbon-carbon single bond are called as conformationals, right? Or you can say the conformers or the rotamers. So why you get these conformers? Because the energy requirement here is very less, right? If there's a free rotation, and you can get different conformations, and the energy difference between those conformations is very small. At room temperature we have sufficient amount of energy that can cause the rotation around the carbon-carbon single bond. So due to the free rotation around the carbon-carbon single bond, these hydrogen atoms attached to it will have different spatial arrangements, different relative positions. Let's have a look at this molecule. You can see here, due to the free rotation around the carbon-carbon single bond, we get eclipsed and the staggered conformation. This one is a staggered conformation when it is in the opposite side, and this one is an eclipse, because here all the hydrogen atoms are eclipsed. Now this is staggered, this is eclipsed, right? So this is the interconversion of the one conformational isomer to the another conformational isomer. This can happen at the room temperature because the amount of energy that is required for this free rotation is very small, right? And that is available at the room temperature. The amount of energy that you require to change one conformational isomer into another is just 12.5 kilojoules per mole. So this is how we represent the different conformational isomers. This is a Sawhorse projection. Here you can see the two carbon atoms. Let's say this is our front carbon and this is the back carbon, right? This is our front carbon and this is our back carbon. Due to the free rotation around this carbon-carbon single bond, you will have different relative positions. Let's concentrate on these two hydrogen atoms over here. Alright. Now you can see these two hydrogen atoms, they are on the opposite side. Correct? If you do a 60-degree rotation, then what will happen? These atoms will overlap. You will have another conformation which is eclipse. Correct? Now here in this case, you can see all the hydrogen atoms are eclipsed, right? All the three hydrogen atoms are in eclipsion. So this hydrogen and this hydrogen, this is under eclipsion. This one and this one under eclipsion, right? And this is a Sawhorse projection. This is how we represent the eclipse state. We can represent the eclipse state in the Newman projection also. And how we do that? You take a circle which actually represents the back carbon, and this one center here represents the front carbon. Now this is our front carbon and this is our back carbon. Now the atoms attached to the front carbon, you can show it like this. There are three hydrogens, 1, 2 and 3. The hydrogens attached to the back carbon here, again they are on the they are in the eclipse state, so they will be almost under the eclipse here, like this. So you may not be able to see the back carbon atoms, alright, because this is under the eclipse. And the staggered one is more stable. Why? Because here the hydrogen atoms are not under the eclipse, right? You can see this is down here and this is up. Correct? So these hydrogen atoms are not under eclipse. Therefore, you can draw its Newman projection like this. Let's draw the circle as a back carbon, as this one, and the center here means the front carbon, that is this. Let me draw it like this one. Now the front carbon has 3 hydrogen atoms attached to it, and I'll draw it like this, 1, 2 and the 3 here. The back carbon has got 3 more hydrogens, but it's not under eclipsion. Rather, these will be, in this direction here. Now hydrogen atoms are away from each other, so this is the stable conformation of the ethane. Ethane actually has two conformational isomers. One is called as a staggered and the other one is called as eclipse. And you can convert a staggered one into eclipsion by a 60-degree rotation. Suppose if you keep this front carbon there, and let's suppose you are giving a rotation to the back carbon, right? Let's give a back carbon rotation around 60 degree. So what would you expect? You will get a conformation in which all the hydrogen atoms will be under eclipsion, right? The hydrogen atoms will be like this, right? All the hydrogen atoms will be under the eclipsion. This is the front carbon, and now by about 60-degree rotation here to the back carbon only, now all the hydrogen atoms will undergo eclipsion, and you may not be able to see them clearly. Now this is an eclipse. Again, you give a 60-degree rotation to the eclipse, you will get a staggered one. Staggered conformation is more stable because of the less steric hindrance. Eclipse is, unstable one as compared to staggered, because there is, a hydrogen repulsion, steric repulsions will be there. Now have a look at this one. You see, due to the free rotation around the carbon-carbon, single bond, energy changes. The top one here is, this is the eclipsed one, and the bottom one is the staggered one. Staggered is more stable than the eclipsed. You can see here, by 60-degree rotation from eclipsed you get a staggered, and further 60-degree rotation produces the staggered one into eclipsed. So that means if you do a 60-degree rotation here, this hydrogen atom will now eclipse with this one will eclipse here, and this one will eclipse here. And now by a 60-degree rotation in the clockwise direction, you get a eclipse state, right? The same thing you can represent here in Sawhorse projection also. Again a 60-degree rotation. Now by all these hydrogen atoms will be now under eclipsion. This hydrogen and this hydrogen will eclipse, and this one will also eclipse, right? All the hydrogen atoms will now eclipse. Hope you got it. Thanks for watching the video. Bye for now.